Okay, this is the second part of the resistivity video, so it's video 4, part 2 of resistance. In the last video we spoke about the effect that length has in resistivity. So the longer something is, okay, the longer something is, the higher its resistance is, or its resistivity, apologies, its resistivity is. So in the next part of this, we're going to look at the effect of cross-sectional area on resistivity. So I think this makes a lot more sense even than before. So if you imagine a spherical conductor, okay, and always think of current as a, I'm good at these, as a thing that carries charge, right? What I meant to say there is something that carries water, say, through it. Now, if there's charge flowing through here, all these coulombs of charge, right? That's a coulomb, that's a coulomb, that's a coulomb. All these little coulombs of charge. These can travel through here. And we know now the length is an effect on this, okay? Now, at the moment I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 coulombs of charge being able to flow through this at any one time. Enter this little gap and come out the other side, pour out the other side. Now, obviously, if I make this cylinder a little bit smaller, if I try to make this coulomb the same size, the charge is the same size, it looks like I'm probably only able to fit 2. Maybe a little bit more, but at the moment I'm only able to fit 2. So you can see now how the cross-sectional area, this area here on the wire, so if there's a wire running along, there's a wire running along here, and if you were to chop it down the middle like that and look in at this piece of it, so that's what we're looking at here, cut it down the middle, you're going to be looking in that bit. That's what we call the cross-sectional area. So this piece here. So that's pi r squared, the area of a circle, because also wires are circles, cross-sectional area. The bigger the area is, the lower the resistivity, because more charge can get through. Because resistance or resistivity is how much current can flow through something. Okay, it's ratio. R is the ratio of V over I. Okay, and if we have something that allows more current to flow through, then that ratio is much lower. So, moving on from that point then, resistivity, rho, we've come across that before, resistivity, rho, is equal to resistance times area, cross-sectional area in this instance, over L, the length of the conductor. So that tells us, and we figured out that the relationship between resistance is proportional to the length. Okay, as the length goes up, the resistance goes up. Make the thing longer, more energy is required to transfer through. And resistance is inversely proportional to area. And resistivity is given the symbol rho, which is like a little p with a square off the middle, and that line there doesn't attach. And it's measured in the ohm meter. That's the unit, the ohm meter.